All right, welcome back to the deep dive. We're kicking things off today with some seriously impressive work hot off the press from ByteDance Seed. They've just unveiled their new value-based reinforcement learning framework, VAPO. That's value-based augmented proximal policy optimization. And it's making waves.
Yeah, big waves.
This thing just smashed the state of the art on the notoriously brutal AIME 2024 math problem data set, hitting a score of 60.4 using the Q32B model.
Absolutely. And to really grasp the significance, that 60.4 isn't just a small bump, it's like a huge leap.
Right.
Previous top performers like DeepSeek R10 Q32B and DPO were hovering in the high 40s, low 50s.
Yeah.
VAPO has surged past them by over 10 points.
Over 10 points.
And what's particularly noteworthy for us, deep in the weeds of training LLMs, is that they achieved this top score in a remarkably lean 5,000 training steps.
Exactly. So efficient. Okay, so for those of you wrestling with getting large language models to really nail complex reasoning, especially the kind needed for advanced math, reinforcement learning is often the secret sauce.
It's key.
These intricate step-by-step chains of thought are frequently necessary to arrive at those elusive correct answers.
And as we've all seen, the debate around which RL approach is best for these LLMs has been pretty active. Value-based methods, which aim to learn a function predicting the expected future reward for each action, they've always had this strong theoretical appeal, promising more precise optimization and stable training.
But lately, the spotlight has been kind of on value-free methods like GRPO and DAPO.
Right.
They skip directly learning that value function and instead just tweak the policy based on the final reward of the entire reasoning process. And despite the theoretical arguments for value-based methods, these value-free approaches have been putting up some undeniably impressive results.
Yeah, they really have, especially in those long multi-step reasoning scenarios we're talking about.
Which brings us squarely to VPO. The researchers at ByteDance Seed specifically engineered this framework to tackle the long-standing challenges that have, historically held back value-based models in these extended reasoning tasks.
Their core aim, it seems, is to finally realize the full potential of value-based RL in this, let's face it, notoriously difficult area.
Okay, let's break this down real quick for everyone, sort of the 1-minute overview. So the headline here is VAPO, a value-based RL framework from ByteDance Seed, just snagged a new soda on AIME 2024, hitting 60.4 with the Q32B model.
Massive jump.
That's a massive jump, over 10 points compared to leading methods like DeepSeek R10 Q32B and DAPO, and it did it in around 5,000 training steps. Super efficient.
Yeah.
The paper pinpoints the usual suspects that trip up value-based methods with long reasoning chains, value model bias, the headache of wildly varying response lengths, to the ever-present issue of sparse reward signals.
The big three.
And VAPO tackles these head-on with a smart combo of techniques: value pre-training, a length-adaptive GAE, and clever strategies for those sparse rewards, all leading to a training process that's not just effective, but also remarkably stable and efficient.
Precisely. And for us researchers and engineers looking to push the boundaries of what these models can do, understanding exactly how VAPO achieves this performance leap requires us to dig into those key challenges that the paper meticulously lays out in the context of long chain of thought reinforcement learning.
All right, let's dive into the first major hurdle they tackled. This issue of value model bias that crops up over these extended reasoning sequences. What's the fundamental problem here?
Okay, so the researchers highlight a common starting point: initializing the value model using a pre-trained reward model. Now, while this might seem intuitive on the surface, right?
Sounds logical.
It actually introduces a significant initial bias. The core reason, it boils down to the different objectives these models are trained on. Reward models are typically optimized to output a score at the very end of a sequence, specifically at the end of sentence token.
Right.
They're trained to give lower scores to tokens earlier in the sequence because, the full context isn't yet available to make a judgment.
Right. The reward model is essentially just judging the final answer. Makes sense.
Exactly. Now, contrast that with what the value model is trying to do. It's attempting to estimate the total expected future reward for every single token within the sequence, from the very beginning all the way to that end token.
Okay. Different goals entirely.
So right from the get-go, there's this fundamental misalignment in what each model is trying to learn. And the paper meticulously explains how this initial positive bias in the value model then gets amplified during the early phases of training due to the mechanics of generalized advantage estimation, or GAE.
GAE, right.
And its backward computation. This bias essentially propagates backward through the sequence at each time step. It just sort of accumulates.
And they also pointed out how the lambda parameter within GAE can make this problem even worse for long sequences, right?
Yes, that's a critical point. It's pretty standard practice to use a relatively high lambda value in GAE, something around 0.95. Lambda acts as a knob that controls the trade-off between the bias and the variance of the advantage estimate. A high lambda means you're leaning more heavily on bootstrapping, which involves using the value function's own estimate of future rewards.
Okay.
For long sequences, this high lambda causes the actual reward signal, which only arrives at the very end, to be significantly discounted as it's propagated backward. So by the time you reach the earlier tokens in a very long chain of thought, the value updates are almost entirely based on these potentially biased bootstrapped estimates, further undermining the reliability of the value model as a baseline for guiding policy updates.
So for those initial steps in a long reasoning process, the model isn't really learning as much from the actual outcome. That makes perfect sense. Okay, what's the next major challenge they identified?
The second key challenge they delve into is the issue of highly variable sequence lengths that we often see during training for complex reasoning tasks.
Yeah, that's common.
Some generated responses might be relatively concise, while others can be incredibly long and involved as the model works its way through a multi-step problem.
And how does this wide range in length create difficulties for standard reinforcement learning techniques?
Right.
Like with GAE again?
Exactly. The paper emphasizes that using a fixed lambda value in GAE struggles to effectively handle this diversity in sequence lengths. Remember how lambda balances bias and variance?
Mm-hmm.
Well, for shorter sequences, a fixed lambda can lead to high variance in the advantage estimates. You're not looking far enough into the future, basically, to get a stable signal about the eventual outcome.
Okay.
Conversely, for very long sequences, that same fixed lambda can result in high bias. This is because GAE is a recursive calculation. It depends on the value estimates of future states. Over a long chain, these estimation errors can accumulate and significantly skew the advantage calculation.
Right, the errors just build up.
And the inherent exponential decay in GAE's computation just amplifies this issue for longer sequences.
So a one-size-fits-all lambda just doesn't cut it when you're dealing with responses that can vary so dramatically in length. It's either too biased or too variant.
Precisely. You got it. Now, the third major challenge they address is the often sparse nature of the reward signal, particularly when you're employing a verifier-based reward system.
Okay, could you give us a quick rundown of what a verifier-based reward model is and why it typically leads to this sparsity?
Absolutely. So in many of the more advanced reasoning tasks, like tackling math problems, you might have a separate model, the verifier, whose job it is to check if the final answer, and maybe the steps taken to get there, are correct.
Okay, like an external judge?
Kind of. Unlike more traditional language model-based reward models, which might give a continuous score reflecting the overall quality of the response, a verifier often provides just a binary signal. Either the answer is correct, a reward of 1, or it's incorrect, a reward of 0.
Okay. Simple yes, no.
That's the essence of the sparsity. You only receive a non-zero signal at the very end of the entire reasoning process, and it's a simple yes or no. Very little feedback along the way.
And how does the presence of long chains of thought further complicate this reward sparsity? Seems like it would make it much harder.
Well, think about it. The longer the chain of thought, the more individual steps the model has to take to finally arrive at a final answer. If the reward is only given at the very end and it's just binary,
you get feedback really infrequently.
Exactly. Especially if the task is particularly challenging and correct answers are relatively rare. On top of that, generating these long chains of thought is often computationally expensive.
Right, more compute for less reward signal.
So you're spending more resources for even fewer instances of getting that positive reward signal. This creates a classic exploration-exploitation dilemma. The model needs to explore a wide range of potential reasoning paths just to have a chance of stumbling upon a correct answer. But once it does manage to find one, it needs to be able to efficiently learn from that single positive example without getting stuck exploiting potentially flawed reasoning that just happened to lead to a correct answer in that specific instance. It's tricky.
Right, it's like trying to find a needle in a haystack, and you only find out if it was a needle after you've searched the whole stack.
Yeah, that's a pretty good analogy. So those are the three core challenges. the value model bias that can accumulate over long sequences, the difficulties in handling heterogeneous sequence lengths during training, and the sparsity of the reward signal in verifier-based tasks when dealing with long chains of thought.
Okay.
Now let's delve into the specific techniques that VAPO employs to address each of these issues.
Sounds good. Let's start with how VAPO tackles that initial value model bias we talked about.
Okay, so VAPO incorporates two primary techniques here.
Yeah.
And they mention drawing inspiration from earlier work in VC PPO. These are value pre-training and what they've termed decoupled GAE.
Value pre-training. Tell us more about that component. How does it work?
The central idea behind value pre-training is to mitigate that initial bias that stems from initializing the value model with the reward model. They use a two-stage process.
2 stages.
First, they continuously generate responses by sampling from a fixed policy they specifically mention using the supervised fine-tuned policy, or POFT.
Yeah.
Then they update the value model using Monte Carlo returns calculated from these generated trajectories. They keep training the value model this way until key metrics, like the value loss and the explained variance, reach sufficiently low levels.
So they get the value model up to speed first.
Exactly. The crucial final step is to save this pre-trained value model and then use it as the initialization point for all subsequent reinforcement learning experiments. This pre-training phase essentially gives the value model a head start, allowing it to learn a more aligned objective before it has to work in conjunction with the policy learning process.
Okay, so it's like giving the value model some foundational knowledge about expected rewards before it even starts the main RL task. Makes sense. And what about this decoupled GAE? That sounds interesting.
Decoupled GAE is a clever way they've devised to handle the Lambda parameter differently for the value function updates and the policy updates.
Separating them.
Yes. For updating the value function itself, VAPO uses a lambda value of 1.0 in the GAE calculation. This is significant because a lambda of 1.0 results in an unbiased estimate of the returns.
Unbiased, right.
By doing this, they're directly tackling that reward decay problem we discussed earlier for long sequences, ensuring that the value model receives a more accurate signal about the actual long-term rewards.
That makes sense. You definitely want the value function to be as accurate as possible.
Exactly. However, for updating the policy, they use a smaller lambda value. The paper notes that using a smaller lambda for policy updates can actually help to accelerate the convergence of the policy,
Faster learning for the policy.
which is an important consideration given computational and time constraints. In their experiments, they specifically used a lambda for the critic, that's the value function, of 1.0, and a lambda for the policy of 0.95, effectively adopting the core concept from VC PPO of using different coefficients for advantage computation.
So it's like having the value model learn in a more direct, unbiased way, while the policy updates can be a bit more pragmatic, maybe a bit biased, but to ensure faster learning overall. Clever trade-off. Now, how does VAPO address the challenge of those varying sequence lengths? That seemed like a tricky one.
This is where their length-adaptive GAE comes into play, along with a strategic switch to token-level policy gradient loss.
Length-adaptive GAE. Okay, how does that work? Sounds dynamic.
The core idea is to dynamically adjust the lambda parameter used in GAE, specifically for the policy updates, based on the length of the generated sequence. They observed that a fixed lambda, like the 0.95 used in VC-PPO, isn't optimal for both short and very long sequences. We talked about this, right? For very long outputs, the effective weight of the actual reward becomes almost negligible with a fixed high lambda due to that exponential discounting.
Right, because the reward signal from the end gets so diluted as it's propagated way, way back.
Precisely. So they designed length-adaptive GAE with the goal of achieving a more uniform distribution of TD errors. That's the temporal difference error, the difference between the predicted and actual returns across sequences of different lengths.
Uniform TD errors.
Okay. They aim to make the sum of the coefficients applied to these TD errors roughly proportional to the length of the output sequence. This leads to their formula for the policy lambda. Lambda policy equals 1 alpha L.
Whoa, okay, formula time. L's the length.
Yep, L is the length of the sequence, and alpha is a hyperparameter that controls the bias variance trade-off. In their experiments, they set alpha to 0.05.
Hey, 0.05.
What this means is that for longer sequences, lambda policy will be closer to 1, which helps to reduce bias, while for shorter sequences, it will be smaller, which helps to reduce variance.
That's a really elegant way to handle that variability, dynamically adjusting the bias variance trade-off based on length. Neat. And you also mentioned a token-level policy gradient loss. What's that about?
Yes. So traditionally, the policy gradient loss is often computed at the sample level.
Sample level, meaning per sequence.
Yeah. This means that for each generated sequence within a batch of training data, the individual losses of all the tokens within that sequence are first averaged together, and then these sequence-level averages are themselves averaged across the entire batch.
Okay.
The issue with this approach, which they point out, is that tokens originating from longer sequences end up contributing less to the final overall loss value simply because there are more of them to average over at that sequence level.
So if a really long reasoning chain has a critical error early on, its impact on the overall learning might get diluted in that sequence level average, like it gets drowned out.
Exactly. You got it. To address this potential imbalance, VAPO switches to a token-level policy gradient loss.
Token level. Okay.
In this approach, the loss is calculated for each individual token within every sequence in the batch. Then, all of these token-level losses are averaged together across the entire batch.
So every token counts equally?
Pretty much. This effectively gives every single token, regardless of the length of the sequence it belongs to, a uniform weight in the final loss calculation. This ensures that any issues arising in long sequences, which might be more prone during the exploration phase, are not underweighted and can be addressed more effectively during training, ultimately leading to hopefully more stable and robust learning.
That makes a lot of sense for ensuring that errors in those longer, more complex reasoning paths are properly accounted for. Okay, so we've covered how VAPO handles the initial value bias and the varying sequence lengths. Now, let's talk about how it tackles the challenge of that often sparse reward signal. That sounded tough.
Yeah, the sparse reward problem. To deal with the sparsity that's inherent in many verifier-based tasks, VAPO incorporates 3 key strategies: clip higher, positive example LM loss, and group sampling.
Clip higher. Sounds like a modification to the standard PPO cleaning mechanism.
It is indeed. In standard proximal policy optimization, or PPO, the ratio of probabilities between the new and the old policy is clipped within a symmetrical range, right? Usually 1 epsilon, 1 plus epsilon.
Yep, standard PPO.
VAPO innovates here by decoupling this range into a lower clip epsilon, epsilon low, and a higher clip epsilon, epsilon high.
Okay, 2 epsilons.
Crucially, they increase the value of epsilon high while keeping epsilon low relatively small. The rationale behind this is to help mitigate the issue of entropy collapse that can sometimes occur during PTO and GOPO training.
Entropy collapse, where the model gets too confident too early.
Kind of, yeah. By having a larger upper bound for the clipping range, that's epsilon high, it provides more room for the policy to increase the probability of actions, tokens, that currently have low probabilities. This encourages greater exploration of the action space.
So more exploration.
But they maintain a relatively small lower bound, epsilon low, to prevent the probability of these tokens from being pushed all the way to 0 too quickly, which could lead to a premature narrowing of the sampling space. You don't want to close off options too fast.
Right. Makes sense. What values did they use?
In their experiments, they used an epsilon low of 0.2 and a higher epsilon high of 0.28.
0.2 and 0.28. Okay, so it's like gently nudging the model to try out less likely options to encourage more exploration, but without completely abandoning what it has already learned is generally good. What about this positive example, LM loss? That sounds useful for sparse rewards.
Yeah, this technique is specifically designed to make more efficient use of those rare instances when the model actually manages to generate a correct answer.
Maximize the learning from successes.
Exactly. In tasks where the accuracy is typically low, the vast majority of training samples will unfortunately result in incorrect responses. Traditional RL methods primarily focus on suppressing the probability of the actions that led to these incorrect outcomes.
Right, punish the bad stuff.
VAPO adds an auxiliary negative log likelihood, NLL loss, that is specifically applied only to the correctly sampled responses during the reinforcement learning training phase.
NLL on the good ones.
It's essentially a form of imitation learning that encourages the model to further increase the probability of the specific tokens that appeared in those successful trajectories. This additional loss is then combined with the main PPO loss using a weighting coefficient,
A weight.
which they set to 0.1 in their experiments. The core idea is to maximize the learning derived from those valuable positive examples, which are often hard-won through extensive exploration.
That's a really smart way to reinforce those successful pathways when they finally occur. Squeeze every bit of learning out of them. And the last technique they use for dealing with sparsity is group sampling. What's that?
Yes, group sampling. So when you have a fixed computational budget for generating training samples, There are generally two main strategies you can employ.
Okay.
You can sample a large number of different prompts, the initial problems, and generate just one response for each. Or you can sample a smaller number of prompts, but generate multiple different responses for each of those prompts.
Breadth versus depth per prompt.
Exactly. VPO adopts the latter approach, depth. In their experimental setup, they sampled 512 different prompts, but then generated 16 distinct responses for each of those prompts.
16 responses per prompt. Okay.
Their results indicated that this strategy led to slightly better overall performance. The key benefit here, they argue, is that by generating multiple responses for the exact same initial prompt, you obtain richer contrastive signals within that prompt.
Contrastive signals.
Yeah.
Like seeing what worked and what didn't for the same problem.
Precisely. The policy model can learn more effectively by directly observing which reasoning paths led to a successful outcome and which ones didn't, all within the context of the same starting problem. It helps differentiate good versus bad strategies more clearly.
So it's almost like setting up mini-controlled experiments for each prompt within the training batch.
Wow.
Interesting. Okay, we've now covered all the key techniques that VAPO employs to tackle these inherent challenges. What did the actual experimental results look like? Were they as good as the intro suggested?
Oh, yeah. The results are truly compelling and I think really demonstrate the effectiveness of their overall approach. They trained VAPO using the Qwen32B base model.
Qwen32B.
Right, and importantly, for a fair comparison with other methods like DPO and DeepSeek R10 Qwen32B, they ensured that no additional supervised fine-tuning data was introduced during the reinforcement learning phase. That's key.
Good, apples to apples comparison.
For their baseline PPO implementation, they use standard settings AtomW optimizer with specific learning rates for actor and critic, warm-up constant scheduler, batch size of 8,192 prompts, and a standard GAE lambda of 0.95. Pretty vanilla setup.
And then they implemented those 7 key adjustments that we just discussed: the value warm-up, decoupled GAE, length-adaptive GAE, clip higher, token level loss, positive example loss, group sampling to create the full VPO framework.
Exactly, all 7 components. And when they directly compared VEPO to this vanilla PPO baseline, the difference was, well, striking.
Oh, striking.
The vanilla PPO implementation essentially failed to learn effectively during training. It just kind of flatlined, ultimately achieving a very low AIME 24 average at 32 score of only 5.
5, wow.
In stark contrast, VAPO achieved that state-of-the-art score of 60.4.
From 5 to 60.4, that's an absolute massive improvement. Okay, and how did it compare against the previous top-performing methods, the value-free ones?
Yeah, that's the crucial comparison. As we highlighted right at the beginning, DeepSeek R10 Qwen32B achieved a score of 47 on the same AIME 2024 benchmark.
47.
And DPO reached a score of 50.
50.
VAPO at 60.4 surpasses both of these leading methods by a significant margin of over 10 points.
Over 10 points clear. That's decisive.
And as Figure 1 in the paper clearly illustrates, it achieves this peak performance in considerably fewer training depths compared to DPO. VPair reached that top score around the 5,000 step mark, whereas DPO required significantly more training iterations.
Faster and better.
And not just that, the researchers emphasized the stability of VOPO's training process. They reported no training crashes across multiple independent runs.
Nice. Always good to hear.
And the final performance scores consistently fell within the 60-61 range, underscoring the robustness and reliability of the framework. It wasn't just a lucky run.
That stability is huge. Okay, the ablation study they conducted must have been particularly informative for understanding the contribution of each of these new components. What were the key takeaways from that? Do they all matter?
Oh, absolutely. The Ablation Study, which is detailed in Table 1 of the paper, is really insightful. They systematically removed each of the 7 key modifications introduced in VAPO one at a time, and then measured the resulting drop in performance on the AIB24 benchmark.
Okay, taking them out one by one.
Exactly. The results from this study clearly demonstrate the importance and individual contributions of each of the VAPO components. For instance, when they removed value pre-training. Remember that initial step?
Yeah, getting the value model ready.
Without that, the model also essentially failed to train effectively, similar to the vanilla PPO baseline. It only reached a score of around 11.
Wow, so value pre-training is critical.
Absolutely essential, it seems. Removing decoupled GAE led to a substantial performance drop of approximately 27 points.
27 points. Huge impact.
Yeah, highlighting its critical role in effectively handling that reward decay in long reasoning sequences. Taking out length-adaptive GAE resulted in a decrease of about 15 points.
Still significant.
demonstrating its effectiveness in balancing the optimization process across sequences of varying lengths. And each of the other components, clip higher, token level loss, positive example LM loss, and group sampling, also contributed positively to the final performance. Their removal led to performance drops ranging from about 5 to 7 points each.
So they all pull their weight.
Definitely. This really underscores that VAPO's significant success isn't just one magic trick. It's a result of the synergistic effect of all these carefully designed and integrated techniques working together.
Right, the whole is greater than the sum of its parts. And the training dynamics curves presented in Figure 2 of the paper, what key insights did those provide when comparing VAPO to DAPO?
The training curves, they compare the performance of VAPO and DAPO and offer further valuable insights into the training process. VAPO's training curves for both the reward score and the average response length exhibit noticeably smoother trajectories compared to those of DAPO.
Smoother, indicating more stability.
That's the interpretation. It suggests a more stable and robust underlying optimization process. Figure 2a also indicates that VAPO achieves better length scaling, which, as the researchers point out in the paper, is often a good indicator of improved generalization capabilities.
Better generalization. Nice.
Furthermore, VAPO's reward score shows a more rapid rate of increase during the initial training phases.
Learns faster at the start.
Which is likely attributable to the value model providing more granular and effective feedback to accelerate the learning of the policy. That value signal seems to really help.
Makes sense.
Interestingly, Figure 2c shows that the generation entropy of VAPO drops to a lower level in the later stages of training compared to DAPO.
Lower entropy. Is that good or bad? Could mean less exploration.
That's the potential concern, yeah. A very low entropy can sometimes hinder further exploration. However, in VAPO's case, it appears to primarily contribute to increased stability and reproducibility of the results without significantly negatively impacting the final peak performance achieved. So maybe a worthwhile trade-off here.
Fascinating. So VAPO really does seem to represent a significant step forward for value-based reinforcement learning in this challenging domain. The paper also briefly touches on related work in the field. How does VAPO fit into the broader landscape of current research in this area?
Well, the paper strategically positions VAPO as the first value-based reinforcement learning framework to demonstrably outperform the current state-of-the-art value-free methods.
Like DeepSeek R1 and DPO?
Exactly, like DeepSeek R1, which utilizes GRPO and DPO, specifically on these demanding long chain-of-thought reasoning tasks. They provide brief mentions of other relevant research efforts, including OpenAI's O1, Dr. GRPO, and ORZ. And notably, they point out that ORZ, which also adopts a value-based PPO approach, but relies on Monte Carlo estimation instead of GAE for its value estimation.
Different value estimation method.
Right. ORZ only managed to achieve performance that was comparable to the existing value-free methods, not better.
So VPO's GAE-based approach, with all its modifications, seems key to surpassing the value-free method.
That seems to be the implication. This comparison really highlights VAPO's unique and significant contribution in finally unlocking the potential of value-based RL to exceed the performance of the current leading value-free techniques in this particularly challenging area of complex reasoning.
All right, let's bring this deep dive to a close then. What would you say is the most significant takeaway from all of this research on VAPO? If people remember one thing.
I think the key significance of VAPO is that it represents a major breakthrough for value-based reinforcement learning, specifically in the context of long chain-of-thought reasoning for large language models.
Breakthrough, yeah.
For the first time, we're witnessing a value-based framework not just keeping pace with, but demonstrably and significantly outperforming the previously dominant value-free approaches. And it's doing this while establishing a new state-of-the-art on a very challenging benchmark and also exhibiting efficient and stable training characteristics. It kind of ticks all the boxes.
So for our technically minded audience, the AI researchers and ML engineers out there listening, the crucial takeaways here are the critical importance of directly addressing those inherent challenges that arise in long code RL. That accumulation of value model bias, the complexities of handling diverse response lengths during training, and the persistent issue of effectively dealing with sparse reward signals.
You have to tackle those directly.
VAPO's remarkable success clearly demonstrates that by tackling these challenges head-on with innovative techniques like value pre-training, length-adaptive GAE, and specifically targeted strategies for mitigating reward sparsity, well, we can unlock significantly greater potential in applying reinforcement learning to enable much more sophisticated and reliable complex reasoning in our AI models.
Absolutely. This work provides compelling evidence that value-based methods, when thoughtfully designed and optimized to overcome their inherent limitations in long-horizon tasks, can indeed offer a higher performance ceiling compared to the currently favored value-free alternatives in this critical area of AI development. Maybe value-based wasn't dead after all for this stuff.
Right. That leads us to a final thought to chew on. Given the impressive achievements of VAPO, what are the potential future directions for value-based RL as we continue to push the boundaries of artificial intelligence and tackle even more complex reasoning tasks?
Good question.
Could the inherent stability often associated with value-based methods become an even more critical advantage as our models and their required reasoning chains grow longer and more intricate? Will that stability become paramount?
It very well might. As things get more complex, stability is gold.
It certainly gives us a lot to consider as we continue to explore the ever-deepening landscape of AI research. Thanks for joining us for this deep dive into VAPO.